All right, welcome back to Intro to Machine Learning Level 1, Lecture 14. This is a Northeastern University course called DS 4400. Now, today we're going to continue with the idea of classification. Specifically, we're going to cover two more algorithms. One is called K-nearest neighbor, KNN, and the other one is support vector machine. This is Professor Wu, so let's get started. So today we're going to learn two more classification methods. K-nearest neighbor, very easy algorithm, fast to learn, simple to implement, reasonably accurate in prediction. Support vector machine, SVM, is perhaps one of the most famous earlier classification algorithms. Like the first generation, like one of the most famous first generation classification algorithm. The idea is not difficult to understand, although you would need to know some elementary geometry as well as linear algebra. It is quite accurate in predicting, right? Especially when you kernelize it. Unfortunately for this class, we're not going to cover the kernelized version, but it's a good. We'll still cover where like a good starting point. So let's get started. K-nearest neighbor. Okay, let's we're going to stick with the theme of binary classification. Well, it allows us to look at the data, right? Binary is just yes or no. Okay, let's assume that we have some historical data that contains two factors. Along two factors, along with if the student will make into a good college. Okay, so the student's grade versus how good they are in sports, and then 0 is they didn't make into a good college. 1 is if they made into a good college. Again, I just made this data up. It has nothing to do with reality. So, anyways, given this historical data, right, you're given a new student, 0, 0. How can you essentially look at the previous data and conclude whether the student is going to go to a good college? That is, whether the student is going to have an output of 0 or 1. Okay, so now um, one way, right? One way you can do it is basically look at the other students with similar scores and use their outcome as the prediction. And that's basically how k-nearest neighbor works, right? When perform k-nearest neighbor classification, you essentially pick k number of neighbors and simply classify the new point based on the most common category. So, for example, we have A, right? E and A, those are the 2 points, and they are labeled 0. And then we have CD, which label 1. So these ones made into the good college, these ones did not. Okay? Now, based on this information, we have a new point, B, which is right here, at 0, 0. Okay? Well, you will essentially look at the nearest neighbor, which would be this one, and then say, well, what is their category? Well, if their category is 0, you will assign B the same category as them. And that is basically it, right? Now, K, if K is equal to 1, right, B would just look at the nearest neighbor. If K is equal to 2, then it's going to look at 2 of the nearest neighbor, which would be A and E. Now, if K is equal to 3, then you will pick the 3 nearest neighbor. Okay? So these 3 are the nearest neighbor to B. And then you will pick the most common category. So this category is 1, 0, 0. So the majority will be 0. Hence, you will set B to 0. Right? And 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 basically that's it. It's a really really simple algorithm. All you really need is to be able to find the distance. And normally we use the L2 norm for distance. So you essentially, right? You essentially would just, given a point B, make a table of all the distance, pick the one with the shortest distance, and like use the label similar to it. K-nearest neighbor is a very simple algorithm that is theoretically simple to understand. Right? It's a simple algorithm and it performs quite well actually for relatively simple cases where different categories are neatly separated. See how different categories are neatly separated. Therefore, for those cases, K-nearest neighbor performs quite well. Now, K-nearest neighbor could be used for classification and regression, even though we're doing regression. For you can actually use this for even though we're doing classification, we can use it for regression as well. The way it will work is that if you have the nearest neighbors, right, and this is some value A and this is value B, right, you with uh, um, with k nearest neighbor, you will simply average the label for each one of them. So let's say this is your point, and these two are the nearest neighbors. And the result is 8 and 9, right? And therefore, you will assign this 8.5. And that's it. So you can indeed also do regression. With k nearest neighbor, you only have to answer two questions before you use the algorithm. The first question is, what should the k value be, right? How many should you pick? Should you always pick just the nearest one? Should you use the nearest two, nearest three, right? There's a general rule of thumb. Larger k value, right? The more you pick, tends to give you better results, but not too large, okay? So the general rule, people tend to use square root of n. Therefore, if you have n samples, k is square root of 2, square root of n. So if you have 100 samples, then you will pick square root of that, which is 10. Okay? And then the second question is, which distance is most appropriate? For the most part, we just use L2, but depending on the situation, maybe L1 or L infinity might make more sense. So here, given the previous data, right, and now we want to classify point B. So what we do is, once we have B, we measure the distance between B and E, B and A, B and C. So we measure the distance for every one of them. So we know the distance, right? Once we know the distance, right? Well, what is the label for E and A? 0. What is the labels for C and D? 1. Once we have this table, right, depending on the K value, let's say K equals to 1, right? So you pick the one that's nearest to B, and then you assign whatever label it is. If you have 2, right, if K is equal to 2, then you pick 2 of them and assign the most common label, which in this case again is 0. So that's it. That's how K nearest neighbor work. It doesn't get easier than this. It's a really, really simple algorithm. Okay. All right. So now we're going to move on to a harder algorithm, support vector machine. Now, support vector machine is also known as SVM. It's one of the earliest major classification technique. It was invented by Dr. Vapnik. It's actually really, really beautiful mathematically, and there are multiple versions of it. Okay, so the simplest version is linearly separable classifier. That's the simplest one, which we're going to learn. After that, there's this thing called a soft margin classifier. We'll learn this one as well. The one we will not learn is where we have nonlinear boundary classifier. This one, I will leave this to a higher level class. Okay. In this case, we're going to focus on the two most basic version, the ones in red, right? And let's go. So before we understand SVM, the key, like first, you really do need to understand some linear algebra, and specifically the concept of projection, right? With as well as unit vectors. I think in this class we talked about unit vectors already, where a unit vector, if you have a vector v, a unit vector is a vector which we normally denote v hat where the length is equal to 1. Okay, so if you measure the L2 norm, the size of this vector is just equal to 1. All right, how do you get a unit vector? Well, I don't know if you learned that yet, but we'll go over that. Okay, you also need to know projection. Now, other part, given point C, right? If you point C and the vector U, if you want to draw a perpendicular line, right? How do you know the location of intersection? So these are the questions that you need to make sure you have clear in your head before we even talk about support vector machine. So I'll do a quick refresh. Hopefully you knew this already. If you don't, you want to pay attention. So what is a unit vector? A unit vector is a vector of length 1. Like in the picture, this is not a unit vector because the length is not 1. This is a unit vector because the length is 1. So is this one. Length is also 1. Okay? A vector is not a unit vector. If a vector is not a unit vector, we can always convert it into a unit vector by dividing by the vector by its length. So we can convert this one into a unit vector by dividing all the numbers here by the length itself. So, for example, this vector is 3, 4, so this must be 5, right? 3, 4, 5. So this right here is the length. And the coordinate of this is 3 by 4. Well, if you want to normalize this or make this a vector length of 1, all you have to do is divide this by the length, which is 1/5. And now you have 3/5, 4/5. Now together, this now means you have a unit vector. And you can check this. If we measure the size of this with L2 norm, the size is indeed 1. So after you convert this into this, the size become 1. The process of converting larger vectors into a unit vector is called vector normalization, or just normalization. When a vector v is normalized, we like to denote with a v hat. Okay, so v hat. Now, quickly, let's pause the video and see if you can normalize this. If you normalize it, you should get a vector like this. Okay, pause the video, make sure this makes sense to you. Okay, so let's move on to the concept of projection. So with projection, given a point C and the vector u, point C and the vector u, okay? If you want to draw a perpendicular line from C down, so that this is perpendicular, from C to U, well, first question, what is the distance from 0 to this point? What is this distance right here? Well, it turns out that this distance is simply the vector v. So this is vector v right here. V times the vector u normalized. Okay, so this distance, which is d, from here to here, this distance here, d is equal to v times u hat. What that means is if you are drawing a line from here to here, first thing you do is you take u and normalize it. So if you're drawing a line from v to u, first thing you do is you normalize u. Once you normalize u, you take the dot product between u hat and v, and that gives you the distance. So the equation for this is just the inner product. Now, see if you can get the same distance using this equation. Okay, so let's say we have u hat is, what is it, 4 by 2? 4 by 2. And then after you normalize it, then it becomes 4, 2, 1 over square root of 20. Okay, now if we do the dot product of u with v, so u with v, u hat with v, notice how the result is roughly 3.13. So that's what that's saying here is this distance from here to here is 3.13. Now if we look at this number, which is 3, right? 3.13 for distance here to here makes sense. Makes sense. So this is how you calculate the distance when you are drawing a line from a point of a vector onto another one. The process of doing this is called projection. It's projection. It's almost like pretend you have the sun here. Here's the sun. And the sun ray is coming down and is casting a shadow. And D is essentially the size of the shadow. Okay? So projection. This is called projection. Now that we know the distance here, right? What if we want to find this exact location? Well, that's also really, really simple. If we know u hat, which is how far this is, right? U, the vector, hat. So this vector is length of 1. All we have to do is multiply d by u hat, and we'll get this point here. We'll get d here. So as you can see, if we multiply d, which is this, by the vector of length 1, that will give us capital D, which is right here. And D, I told you previously, we got the distance by taking the inner product of the u hat and v transpose. Now, given this equation, we can now identify exactly what this location is. Remember, I told you D is roughly 3.13. We calculated that right here. After we calculate 3.13, right, like all we have to do is multiply this by the normalized u. Okay, so this right here is 3.13. If we multiply this by the normalized u, that will give us the point D. Okay, that will give us point D. So let's do that. We multiply 3.13 by the normalized version, and it's saying that D is at 28, 2.8, and 1.4. Now, if we look at this carefully, this is saying at this point is 2.8 and 1.4. So it's saying this point, 1.4. So you can see that we just essentially identify the point D. Okay, so this is a very brief and very quick review of the projection and how you can get distances. All right, the idea is if you have a vector v and you want to project or cast a shadow onto another vector, you now know how to find the distance as well as the point of intersection. Okay, so that's the point of this whole thing of projection. And you need to know projection essentially in order to understand SVM. Ideally, you've already reviewed the concept of projection, and that this is just a review. But let's go on. Now we're ready for support vector machine. Now remember, we're doing classification, and specifically binary classification. So we have two classes, the red dots and the blue dots, right? Two classes. And we want to somehow have a function such that it classifies either one class or the other. Okay? Now, in the basic case, with SVM, it assumes that you can separate the data with some kind of line. Okay, so it's linearly separable. That's what that says. Okay, so what would be a simple rule that allows us to categorize these two classes separately? Well, one way is essentially to project all the data. So project the data onto a line. So let's take this point, for example. If we want to project this data onto this line, it will end up here, right? Now, if we want to project this onto this line, it will be right here, it will be right here. So we can project onto a line. This projects right here, this project here, and this project right here. Once we project onto a line, we can essentially set a threshold. We'll call this B. And then if the value, the distance between the distance is greater than B, right? You can see if it's greater than B, like this one, then we can categorize that as the blue class. Now, if the distance from here to the red point is less than B, then we can categorize them as red points. So that's like one way of how you can do that. And actually, this is exactly what I wrote here. So you essentially project these points onto a line. Now, the problem is which line? So we're going to call the line W, okay? How do we know the best line to project? And if we know, how do we know the best B to essentially set the points? So if you have an SVM algorithm, the way it essentially works is they project everything onto a line, and then you can either a line or plane or hyperplane, depending on the dimension of your data, and depending on if the projection is greater than B or less than B. Greater than B, it's class blue. Less than B is class like red. So how do we find this line, right? Obviously, we can draw the line W many different ways, right? We can draw it this way. That would not be a good idea. If we do it that way, notice the projection will end up here. So the red and blue will essentially just mix with each other. Or if we had drawn it this way, well, that's slightly better. See, red and blue are separable. Therefore, we can pick B here. But I wouldn't say that that's the best way projection. Ideally, you want something more like W3, where after you do a projection, there's a good amount of gap, right? Gap between the two classes. So ideally, that's the case. So how do we then go about finding this W vector if it can point essentially any direction? Well, it's not immediately obvious how we can pick W. There are many, many ways, right? So first, let's denote each point. I'm going to first denote each point as xi. So xi, x1, x2, x3, x4. So the points, I'm just going to give them a name, x1 to 4. Okay? And therefore, we know that the distance from 0 all the way to the point of projection. So like from if I were to project this onto W3, for example, right? So the vector would be here, and after the projection, it will be right here. We know that the distance here is equivalent to xi, so this is xi, times W3 transpose normalized. This is equal to D. So we just learned that. Like the idea that you can find the distance after projection. So we have an equation, which we know how to find the distance after the projection, di. Note that we have normalized W hat instead of W. Remember, we had to do a projection onto a normalized version. So that's how you got the D. Therefore, we can perform classification with a rule, right? If after the projection, right, after the projection, if it's greater than b, some point b, after the projection, if it's greater, then it's going to be group blue. And after the projection, if it's less than b, right, then it's going to be red. So that's how, that's how it could work, right? In SVM, like in logistic regression, I think we put 0 and 1. But in SVM, we tend to like to pick 1 and -1. Okay, so the two classes are -1, 1. You'll see why later, that this is a more uh, convenient way to do it. Okay, so the classification rule is therefore this minus b, if it's greater than 0, we pick blue. If this minus b, because I mean move the b here, if it's less than 0, then it's red. Okay, so that's the classification rule. That's how we can set things apart. So how do we find w? Well, given that the label is either y equals 1 or y equals -1, and we also identify the classification rule, how can we find the best w that give us the best classification result? Well, notice that when we have the blue point, which is y equals 1, it implies that with the correct w, we should get this. So the blue point implies that w times x minus b should be greater than 0. That's what blue implies. Therefore, the correct w would imply that this right here, if it's greater than 0, right, multiplied by 1 should be greater than 0. Because y, right, if it's blue, is going to be 1. If it's blue, this should also be 1. Therefore, or at least positive. So this should be a positive value. Therefore, a positive value times 1 will give us a positive value. Now, I think that part is a point where people get confused. So let me slow down and try to explain that same concept again. Okay. Notice that when you have a blue situation, so these blues are 1, these red are -1. Okay, that's how we label them. So we have a blue situation. With the blue situation, as I showed you previously, this condition must be true. If this condition is true, then this value must be a positive value because it's greater than 0. That's like what it's saying. So if we have a value greater than 0 multiplied by 1, then it has to be a positive value. Okay? So that's observation 1. Okay? This is where most people get lost. So you want to go over this logic. Maybe pause the video and think about it for a bit. Now, notice in the second case where we have the red points, where y is -1, it implies that with the correct w, we should get this, which is the second condition. Therefore, this part must be negative. Okay? If this is negative times another negative will give us a positive again. So this implies that the two classes have the same way of determining correctness. Regardless of whether we're talking about red or blue, this equation here, where you have x project onto w minus b, whenever we take this, multiply by yi, the label, it should always be greater than 0. And if it's not, you made a mistake. Okay? So this is the part you pause the video because this is how we define the error, right? This not error, but in this case we're defining correctness. If this is greater than 0, it means correct. If it's less than 0, which is negative, it means it's wrong. So, okay. How do we find W? We've been asking the same question again. Well, now that we have come to this conclusion, well, if we have n samples, then the larger this value is, right? The larger this value, that means more correct we are. And the more negative it is, that means it's wrong. Therefore, we want to find the W and B, such that the correctness is maximized. Okay. Now, if you don't remember, if you forgot, like why does this measure correctness? It measures correctness when it's a positive value. And you got an incorrect, it becomes a negative value, right? Therefore, if you sum up all the n samples, you want it to be as positive as possible. And if you get a negative, it means you're getting wrong classification results. Okay, so this equation here is essentially how you measure correctness, and you want to maximize the correctness. Okay, notice that every time you got the wrong answer, you will get a negative value, which will lower your cumulative score for correctness. All right. Now, there's a problem here. This right here, if we want to find the optimal normalized vector, that gets kind of hard, right? It's not easy to find a normalized vector, right? So we can simplify this a bit by, instead of finding the normalized vector, let's just find the best vector for now, just the best direction. And then we'll leave the normalization to later, right? Once we find W, we can normalize it afterwards. Now, there's this one problem. This right here kind of allows us to find W. But even if you pick the best W, look, if you have picked the best W, you could still end up with multiple B values. You can have B here, right? If your B here, you're still going to get perfect classification. If your B value is also here, you're still going to get perfect classification. So essentially, you have infinite possible B values between these 2 points. So we are not able to get a B value, a unique B value, because there's a whole range, right? In fact, you can just draw a line here, which is very close, and you still will have perfect classification. Because as long as anything is greater than B, you put it to blue. Less than B, you put it to red, right? So my point here is you can pick a lot of B values, but visually you can tell that it makes the most sense to pick the B value directly in the middle. So how do we adjust the objective we have so that we make sure that we always pick the middle point between the two margins, right? How do we do that? Well, how do we find B? Before we jump into this idea, how do we find B? Right? We wanna, I want to define some vocabulary. So let's say we have class blue and class red, right? We're gonna define the point that is closest to the other class as the support vectors, right? The point here is a support vector, right? That's the name for it. And with two classes, right, we will have two support vectors. So XB and XR. So these two, XR and XB. So these are the support vectors. And we're going to call the distance between B to the support vectors as the margin. So this is margin, M. Okay, so we know that for support vector machine, SVM, ideally we want to pick B exactly in the middle between the margins. No, but if we don't normalize W, okay, so hopefully you follow to this point. Next, remember we instead of trying to find this here where we are normalizing, finding the normalized W, we are no longer normalizing W. Okay, so we need to adapt. We need to adapt the situation such that we are not normalizing W anymore. Okay, so we're not normalizing W anymore. Okay, note that if we don't normalize W, when we project XR, and XB, when we project them onto W, it's no longer going to give us the distance, right? It's not going to give us this distance or this distance anymore. Okay? Over here, let's look at the equations. We can, yeah, it will not give us this. So that's the key. No, if we are not projecting onto normalized vectors, we can't guarantee that it's going to give us the distance. Okay. Now, we can mathematically describe the margins. So I told you the margins M and M. Okay. So we can describe the margins as A minus B. So A minus B is essentially this distance. Or B minus C. That will also give us the margin. Okay. So there are two ways to identify the margin. Now, I just told you what is A. Well, the distance A should be XB project onto W normalized. So the distance here, let me see if I can write it this way. So this distance here should be XB project onto W, but the normalized version. That's how we got the distance. Okay? So that's how I got A. How do you get from distance from here to A? Well, you project B onto W hat. B, W hat. So that's how I got A. After that, how do we get C, right? The distance to C. So B minus C will give us M again, right? So how do we get C? Well, C is XR project onto W hat right here. Now, if we normalize W into W hat, that's how we would get the margins. That's how we get the margins. But we didn't. Remember, we didn't really normalize W. So what happens? Like we wanted to simplify. We just want a vector instead of a normalized vector. Well, in that case, when we have this minus B, it's no longer M. Instead, this margin is a different value. We don't know what that value is. I'm going to call it K. So previously, this is the equation. So now, instead of M, we're going to get some other value K. Over here, equivalently, right, instead of M, we're also going to get some other value K. But the two Ks will be the same, right? Because it's just it's equally different on both sides. Which yields the expression that I can just switch this with K, give us this. Now I can switch this with K again, which give us this. Now we have all the necessary relationship. This is the relationship that we want. Okay. We can combine all these relationships into one equation. Okay. If we combine it into all one equation, so this is what we just came up with. If we had normalized it, it would have given us m, right? Normalize it would give us m. But if we did not normalize it, that was essentially the result we got instead. The total distance between the two classes is 2 times the margin. So margin 1, margin 2. So 2 times the margin is equal to this part plus this part. Okay, so 2 times the margin. The equation came from here. So if that's 2 times the margin, we can combine them together and notice that b gets canceled out. There's no more b. And the resulting is just this minus this. Okay, now these are the normalized version, okay? So we can write out the normalized version and recombine them. If we recombine this, it becomes this here. All right, take a second. See that if I recombine them, this whole expression can be written this way. Okay, now we can plug equation 2, these equations now, into this one and this one. If I plug them in, then KB will go here, B minus KB over here. Once again, this came from the equation for 2 times the margin. If we combine them together, the B once again cancels out. We got 2K. So in SVM, we essentially want to identify the B, right, such that it gives us the largest margin. So we want this is the equation for the margin. So we want to find B, but there's no B here, right? But what we do know is we want to pick the W that makes the margin as large as possible. So all these work that we did is essentially to come up with the equation for the margin. So this is how we can measure the margin. Well, once we know W, right? Once we know W, then we can always normalize W to get W hat. And then we can pick the middle point between the margins. So once we know W, we can also pick B, because then we know the middle point. Okay. Now, we have two conditions we want to maximize. The first condition, this is the correctness. We want to maximize the correctness. This right here is the margin. So we want to draw a line such that the labels are correct and the margin between them is as this space here between them is as large as possible. So basically, everything we've done so far is to come up equation that describe these two criteria. Again, the first criteria, we want to pick it so that it will draw a line such that after you do the projection, you get correct labels. So that's what this is. The second equation, we want to maximize it. We also want to pick a line, W, such that the margin between the two classes, right? Here's the support vectors. So the margin between them is as large as possible. Now, let's look at this very quickly. When we're trying to maximize this, I told you the constants don't matter. So we can actually just ignore the constant. Once you ignore the constant, I also told you squaring it doesn't matter. So we can just square it. Lastly, we can convert maximum into minimum by flipping it. So This is a much easier way of writing the same thing, where we're just trying to minimize this objective. And then, so that was the second objective. Now let's look at the first expression. Well, maximization, we can convert it into minimization by just putting a negative here. So now we have a situation where we are trying to minimize instead of maximize both objectives. And we can essentially minimize both of them simultaneously by putting this here and here. So the combination of the two of them we want to minimize. Now, over here, right, I told you previously, we don't really have to worry about B. As you'll see in a little bit, B is actually going to get canceled out when you do gradient descent. So you don't even need B. But B can be easily found once we know W hat. Okay, so we can find this afterwards. Lambda here is a hyperparameter, which you will set. You can just set it to 1, but the larger the value, right, the more important you want to make sure the label. So this is the correctness, right? And this is the margin. So do you want the correctness to be more important or the margin? And like depending on how you pick lambda, you can control the trade-off between correctness and margin. Okay? All right. So running gradient descent with a simple SVM objective. So once we have SVM, we all know how to run gradient descent, right? We're trying to minimize this. So to calculate the gradient of this, it's quite easy. Well, the norm, we did this on the exam, so you should know how to calculate the norm square of a vector, which is 2w. Okay, so that's the derivative for this. Now, let's calculate derivative for this with respect to w. Well, you just cancel it out. It's yi xi. So that's it. This is pretty easy, right? So that's the derivative for the simple SVM case. Now, I'm going to rewrite this as x1, x2, xn. So notice this and this are exactly the same, right? xi is a vector. So yi is going to multiply by this vector, add on to y2 multiplied by this vector. So that's why these two expressions are the same. Now, since they're the same, each one of them is a vector, right? So remember, the matrix X is x1 transpose x2 transpose. That's how we represent bunch of data. Therefore, this one here is x transpose. Right? Now, write this together. X transpose times y, where y is this entire vector here, 2w. So the derivative is really easy to find. Like now that you know the derivative, you can essentially run gradient descent and then solve for w. You'll find the optimum w. Once you get the w, you can now calculate w norm. So just normalize it. And then once we have w norm, we can now calculate the margin. Now remember the equation for the margin. You will essentially project the support vectors. So you need to find the support vectors. You need to find the vector that's closest to each other, right? So essentially you have to go through every single point and figure out the point that's of one class that's closest to the other class. Okay, so that gives you M. Now that you know M, right, you can find D from 0 to B, the distance from 0 to B as the margin plus plus W R transpose W. I think this should have been a hat. Okay. And this allows you to find the B point, right? Because you know this whole thing and you can just calculate this. So quick recap. We did a lot of geometry, and the whole point of these geometry manipulation is to come up with a way to measure correctness versus margin. And with SVM, we want to get the correct labeling and we want to maximize the margin. And once we do that, we came up with this objective. And this objective is pretty easy to solve because the gradient is easy. Okay. Now, I wrote the code for you guys. Um, these are the points, right? I have 6 points here. And it essentially, what I did, yeah, I ran gradient descent. And the final result, you can see, it's able to pick W, and it's able to pick the point B, which is essentially the center, right? You have two margins. So this is margin one, margin two. And over here is the support vector. Support vector. Right? So you can see that this did a pretty good job. And when I asked it to wait, did I do classification? No. Yeah. Well, you can see that this will do a good job anyways. So go and study the code for this. See so that you can also do this. Okay. So I've for this code, I actually recorded a video for you guys as well of how gradient descent will look over time. Let me see if I can get the video out. Let's see. All right. So in the beginning of the gradient descent, it's not very good, right? Obviously, it's not picking a good W. And as you run gradient descent, it's picking a better and better and better W, and it's picking a good B point. Right? It's picking a better B point, better W, better B. So you can see all the points to the right of the B, the red dot, we can classify them as one class. And all the points to the left, we can classify them again as the other class, right? So you can see this in action. It's literally trying to find a line such that after you do the projection, you can divide them into two sections, left and right. Okay, so let me. Yeah, the video is basically done now. Okay, so that was the video I wanted to show you. Next, so we worked through the most basic case. What we just did was, oh, oh man, I think my my video started playing. Okay, all right. Well, whatever. You guys will forgive me. I'm not going to record this whole thing over again. Anyways, we went through the most basic case of support vector machine, which results in this objective. So this objective. Now, there are cases, right? There, so this is the objective. Notice that if we get the correct prediction, then this whole thing will be negative. Okay, which is good because we are trying to minimize, right? So getting it correct will make it negative, right? So again, we got it correct. It's a negative value. Therefore, the more we get correct, the more negative it's going to be. However, if we already have a correct prediction, honestly, if we make it more negative, it's not going to help the prediction. So we just care that we made the right prediction. We don't really care that it made a very, very right prediction because it's binary anyways. Yet, yet, for this particular case, if it is more negative, it's favored. So I think the point here I'm trying to make is that this objective here is going to really favor big negative numbers. Whereas we don't really care if the negative is really, really big. After a certain threshold, correct is correct, right? So you don't need to be very, very negative. So we don't want the objective that's given so much favorable attention towards really, really negative values. So this is not I mean, it will work, as you just saw, it will work, but you can get even better result if you were to take into account that we just need a negative, big enough negative. We don't need it bigger than necessary. Okay. Therefore, what we're saying is that the objective cares too much that more negative is better. What makes more sense if we only penalize the objective if we get the wrong prediction. So we should really put more focus on the mistake, right? We want to penalize this when we make a mistake, and when we make a correct one, if it's correct, there's no need to make it more correct. Okay. So the way we can make a slight adjustment to this, right, is by converting the original objective and adding a ReLU to it. So, so here's the original. Take a second and look at it. And here's the addition. This addition puts into account that as long as you got it right, you don't really care how right you are. Okay? So I told you previously, if we got it right, right, this is going to be a positive, and this is going to be a positive. So this whole thing will be negative. So if you get it right, it's negative. Now notice ReLU is a function such that if it's negative, it's going to give you 0. Okay? So if you get it right, correct, it's going to be the whole thing will be 0. Meaning it's you getting it right, good enough. It's not going to add to the penalty. But notice if you get it wrong, then this is going to be a positive value. If it's a positive value, then it's going to go into the penalty because you don't want positive, you're trying to minimize. So by adding a ReLU into this mix, right, you're no longer emphasizing getting a really negative value. You're changing the emphasis. You're changing the emphasis so that you really care if you made a mistake. Right? You don't want to make a mistake. If you made the correct prediction, good enough. Okay, that's good enough. Now, take a second, like look at the difference. Okay, and realize in this case, the penalty only exists when we get the wrong prediction. And getting a right prediction basically doesn't add anything to the penalty. Okay, let's add even more assumption into the objective. Right now, we assume that all the samples are correctly labeled, right? But what if we have some sample that are really close to the edge and it's wrongly labeled, right? Normally, when you get data, you think the data is correct. But it is possible that the blue X here was accidentally labeled to be red. So this is red. So for those cases, which mislabeling actually happens quite often in real life, and it will screw up the training process, and you'll end up getting a really messed up like a classifier. So for those cases, you want to be more forgiving, right? In this case, if we get the correct label, what we want, right? In this case, if we get the correct label, then we're just going to ignore it. But maybe we don't want to ignore it completely, right? What we want to do is that if we get the correct label up to some point, so if you got a barely correct label, maybe you should still add a penalty. Okay, maybe you should. But if you got a really correct one, then just ignore those. All right. So so this is more nuanced. Okay, maybe we should still add penalty if we barely got a correct one. All right. How do we still include penalty during correct prediction while keeping the ReLU? Well, the way you can do it is basically add a constant. Now, let's study how this constant could really help. This means that even if you got a negative value, right? If the negative value, if it's less than t, it's still going to be positive. So even if you get a correct label, which is going to be negative, unless it's correct enough such that it's greater than t, there's still a penalty. Okay, so what that's saying is if you get something that's close to the edge, right? How close to the edge is still going to be a penalty. But after like a point t, then you still don't care about it anymore. Right? So it's kind of like a compromise between the two ideas we talk about. In the first case, if you got it right, then they really, really like that. In the second case, it completely ignores if you get it right. Right? In the third case, it's going to only ignore it after some point, right? T. Now, notice, notice what I'm trying to say is that you got to be not just a little correct. You got to be correct enough beyond T. Okay. Now, in SVM, the standard is to pick T to be 1. And this is how it result in a soft margin SVM. And this is the equation that you will normally see when you type into SVM into like Wikipedia or something like that. All right. So for the soft margin version, you can also run gradient descent, which I think you guys should definitely try it. And for sklearn, you can actually just use one single command. And this one single command will allow you to make the prediction. Okay, those are the points we were looking at. Therefore, it's giving you -1 for half of them and +1 for the other half. Okay, so at this point, you've learned two versions of SVM. What I want you to do is, without looking at my version, try, like, I wrote the code for you guys, but try it first yourself without looking. Try to write the code for the first version and see. It's called a hard margin. See if you can do it the first version. I mean, the gradient is pretty easy, right? So you should be able to calculate it. Use the gradient here and the gradient descent algorithm, and you should be able to classify these points. Like, these are very simple points. Now, the real challenge for you is to essentially to write the code for the second SVM. I did not, all right? I did not write the code for you for that, nor did I calculate the derivative. So I'm probably going to put this in the homework. So you have to do it anyways. So make sure you know how to do this. And that's it for the class. So yeah, I'll see you later.